record. All right, we're good. We are live. Here we go. How about notice, oh, let me turn on the pen. Notice that products of the following hang on, I'm going to move this. Products of the following binomials will produce binomials instead of trinomials. Normally, when you multiply a binomial by a binomial, you get a trinomial. Except when you're doing these guys. So here, let's just take a look at a couple. How about if you did, I want to make sure I don't do the same examples that we're going to look at. There we go. Suppose we did x plus 2 times x minus 2. So if we foiled that, what's going to happen? Well, you're going to get first times first. You're going to get outside times outside, which is minus 2x. You're going to get inside times inside, which is plus 2x. And you're going to get last times last, which is minus 4. And look what happens. See, right now it has 4 terms in it. But look what happens to the 2 middle terms. What happens when you add anything to its own opposite? You get 0, right? So those 2 middle terms go away. You end up with x squared minus 4, which, as I pointed out, is a binomial. We're used to getting trinomials when we do this. Let's try another one like it. How about if we had, say, 3x minus 2y and 3x plus 2y? Well, if you multiply that out, you're going to get 9x squared for first times first. Outside times outside is 6xy. Let me know if I'm going too fast. Inside times inside is minus 6xy. And what's last times last? Minus 2 times 2 times y, 4y squared. And hey, looky. What happens to those two things? 0. I'm going to say in general. In general, that means, to generalize, to make this kind of a pattern that I can apply to any situation like this. If I have x plus y times x minus y, I will always get, sorry, hopefully you can write a little smaller than me, but I've got to be able to be seen. You will always get x squared minus y squared. And there's fancy names for this. This result here is called a difference of squares. Why is it called difference of squares? Because x squared and y squared are perfect squares, right? The one on the left is x times x, the one on the right is y times y. And these two binomial pairs here also have a fancy name. Resist the temptation to call them opposites. They are not opposites. The opposite of x plus y is not x minus y. The opposite of x plus y would be negative x minus y. if you think about why that is, right? Opposite means completely the opposite. But it is definitely the same two terms, but with an opposite sign between them. Well, again, the word opposite has a more specific meaning than that. It means the whole thing's opposite, not just the first or just the second term. So the term for this is called conjugate. So this is a pair of binomials. So we call this a conjugate pair. And I've always liked the fact that these two definitions here kind of rhyme. Conjugate pairs makes difference of squares. Those of you who grew up reading Dr. Seuss books, that's got kind of a nice little kind of a rhythm to it. Conjugate pairs, difference of squares. People are shaking their heads. It's like, okay, now that's stuck in your head. Good, because now you won't forget it. So conjugate pairs makes difference of squares. And just like everything in math, if you can do something, you can undo it. So if you notice that you have a difference of squares, difference of squares can always be factored into conjugate pairs. So let's move on to example 1. I'll give you a sec to catch up to my writing. Finish off my coffee from this morning here. All right. Probably shouldn't be playing on our phone there, guys. All right, ready? X squared minus 25. I can factor that into the conjugate pairs x plus 5 times x minus 5. And if you don't kind of see right away why that works, FOIL it out, right? X times x would be x squared, and outside times outside would be minus 5x, inside times inside would be plus 5x. The minus 5x, the plus 5x, they're going to cancel. If you like, another way to think of this, and don't write this part down. I'm just going to move over for a sec into scrap paper land way over here. Remember that when you're doing your normal, oh, go away. Ah, no. There we go. Remember when you're doing your normal trinomial factoring, like, I don't know, give me one that's easy. X squared, how about minus 7x plus 12? Okay, how were we factoring that again? We were asking ourselves, we were saying, selves, I know it's x and x, but I'm trying to figure out what two numbers times to make 12 and add to make negative 7, right? That's how we did it. That's how we factored trinomials in 3.5. And then we'd come up with, well, it's definitely minus 3 and minus 4. Well, can I point out to you that I can kind of think of this the same way? I can think of x squared minus 25 as x squared plus 0x's minus 25. I know that's kind of cheating, because what's 0 times x? 0. 0 times anything, 0. So I can kind of treat it the same way. I can say to myself, I can say, self, think what two values multiply to make negative 25, but add to make 5. Well, there's some, 5. I meant to say 0. Sorry, 0, 0, 0, 0. Okay, so 0. So now think about it. If two things add to make 0, what do you know about them? They have to be the same number, but opposites, right? So I can factor this out the same way. I can say, oh, well, it's going to be x and 25. Two numbers at times to make 25. Well, it's either 1 and 25, which doesn't work. That wouldn't add to make 0. Or 5 and negative 5. See, there's a nice logic to that. Now, do I honestly think this way every time I do one of these? Do I think that way? No. I understand that the pattern will always work as long as the first term's a perfect square and the second term's a perfect square. Second term is there we go, is a perfect square. So let's see what they look like when they're a little more complicated. Well, this one's actually just about the same. First of all, it's a difference, right? The word difference means it's a subtract. It has to be a subtract. If you were to ask me, hey, can you please factor x squared plus 81? I'd be stuck. I'd say, done, that's prime. I can't factor it anymore. Right? Because there's no way I could factor it into two binomials. Because remember, if two things times to make a positive, either they're both negative or they're both positive. And if they're both positive, they're going to have an x term in the middle. If they're both negative, they're going to have a negative x term in the middle. There is no way to factor a sum of squares. But back over here in the land of difference of squares, this guy's pretty easy. X plus, x minus, all I have to know is, think, what's the square root of 81? So what's the square root of 81? There you go. Plus 9 minus 9. And again, if this seems like wizardry, feel free to FOIL that out. You'll get plus 9x and minus 9x, and they'll cancel. All right, let's bump this up to one that's a little tougher. 4x squared minus 9 is a perfect square on both of those terms. Because 4x squared square rooted is actually 2x. Think about that. 2x times 2x is 2 times x times 2 times x. You can rearrange those multiplies in any order you want. So it's 2 times 2 times x times x. It's 4x squared. And the square root of 9 is, of course, 3. So therefore, this thing is going to be 3x plus, not 3x, I'm sorry, 2x plus 3 and 2x minus 3. And that's a funny looking 3. And now my eraser stopped working. There we go. Sorry about that. I didn't finish my coffee earlier. I'm very sluggish. Sorry. Let's see if you can think about the next one the same way. Okay, I'll give you a minute, see if you can come up with what this one is. So think like this. Think, what's the square root of the first thing, and what's the square root of the second thing? And if you're looking at them going, well, I can't square root one of them, well, then it's not a difference of squares. But I think I can square root both those without getting any radicals or any decimals. So what should I get? I'll give you a sec to think about this one. Try it yourself. Try it. Did you get, we already know 81 is 9. And what's 16 is a perfect square? Or what is the square root of 16? 4. 4y. 4y. Done. And again, if you're not sure, multiply it out. You'll get a minus 36y, sorry, minus 36xy, and a plus 36xy that will cancel away. All right? And then I look at example 5 and I go, well, wait a minute. 5's not a perfect square. I'm stuck. Wait a minute. What's the first rule of factoring again? What do you always look for? Do you notice there's a common factor here? Take out the 5 first. How many 5s are there in 80? I think it's 16, isn't it? Ah, these two guys are both perfect squares. So once I factor that 5 out, I can list that as x plus 4, x minus 4. What the heck is that? Kello, you gave me a rule about difference of squares. Those things don't look like squares. They're powers of 4. Yeah, but think about this. Think. Isn't x to the power 4 the same thing as saying x squared squared? What do you do with exponents when you take the power of a power? You multiply them, right? So this is like saying 9x squared and 9x squared, and then plus w squared and minus w squared. Oh, look at that. And if you stop there, you've lost a mark. How come? What more can I do with it? Do you see it? That's still a difference of squares. So keep going. I just told you, oops, hang on. We told you a few minutes ago, I can't do anything with a sum of squares. Sums of squares don't factor. But this is a difference of squares. It factors into 3x plus w and 3x minus w. And somebody will say, but why would I lose marks if I stop there? Well, it's kind of like, remember back in grade 5, if your teacher said, hey, make me a factor tree for 36, and you stopped at 3 and 12, right? This has more factors. Keep the tree going. Same logic here. Factor means keep going until you run out of factors. So that isn't done yet. See the logic on that? So that's difference of squares. One more special kind of factoring. The perfect square trinomial. And again, I'm going to start my notes by saying notice. Notice there is a pattern. That's an A. To the products you get when you square binomials. And okay, so let's see. Again, I don't want to spoil the actual question. Oh, they only give us 2 examples of this to do. Okay, so I can make up pretty much anything. So let's square a binomial. How about, well, we started the last one with one like this. So how about we start with, for example, how about x plus 2 all squared? And the question in the chat is, does it matter if you put the negative or positive first? And the answer is no, because remember, you can multiply 2 numbers in any order. So factors, 2 times 3 is the same as 3 times 2, right? So it doesn't matter what order you put the factors. Good question. Okay, so getting back to squaring that. Now, some of you might say, oh, I gotta FOIL this out. I gotta actually write x plus 2 and x plus 2 and then multiply it out. First times first, outside times outside, inside times inside. But you know, there's kind of a, again, there's a pattern to it. You'll notice that you get, for the middle term, you will get these 2 things, 2x, and these 2 things, 2x. So really, you just get this times this doubled. You're going to get 4x. So you're going to get x squared plus 4x plus 4. Let's do another one. See if you can do it by just jumping to the answer without having to go over and FOIL it. Let's say that we do x minus 5 squared. So right now there's probably people going, okay, it's x minus 5 times x minus 5, and you're trying to do the FOILing in your head. No, try not to FOIL it. Just look at this pattern. You could even say it in words if you like. Square the first, double the product of the 2, square the last. Square the first, product of the 2 doubled, square the last. Square the first, twice the product of the 2, square the last. Those of you maybe with like more of a poetic bent, maybe you could turn that into like a haiku. But is that 575? You must square the first, or square the first term now, or something. There's 5 syllables. And then Double the product of the two. That's too many syllables. Double the product of the two. Oh, I'm one syllable too big, right? Haikus are 575. You guys haven't done haikus in a while, obviously. Apparently this is interesting to nobody but me. Okay, fine. Let's just keep going. All right, these were too easy. What if the binomial doesn't have a 1 as the coefficient on the first term? Does my little method still work? Yep. Square the first. Times the two together, then double it. Square the last. So I'm going to actually write this in words. I'm going to say square of term 1. This guy here is the square of term 2. And this guy, I will say, oh, is that 7 syllables? Somebody said double product of the two. Double product of the two. It's still 8, isn't it? Double product of the two. No, that's 7. Oh, good job. Okay, we've got this. The double product of the, I've got to say terms, sorry. Ooh, how about both terms? Both terms. Double product of both terms. Square of term 1. Oh, that's only 4. Oh, well. I'll let you poetic types make that into a nice, good haiku. The side quest of games. Okay, I have the comment, the side quest of games. That's what's happening here? My haiku is the side quest of my lesson? I get that. Yep, definitely. Okay, so guess why we're doing this? So we can do it backwards. Can you recognize when you have a perfect square trinomial? Hey, example 7 looks just like the one I just did. What's the difference in it, though? What do you notice is different about my last example and example 7? The square of term 1. Yeah, that's 5. There we go. We got it. The square of term 1. Double product of both terms. The square of term 2. There you go. Go home and memorize that haiku, and you'll never ever forget how to find how to find a perfect square trinomial. And that's what these are called, by the way. All 3 of these guys are called. Oops! Oh, I didn't mean to cross that out. I meant to highlight it. There we go. All 3 of these guys are called perfect square trinomials. And I recognize them because notice that what's different about this one is that it's got a plus instead of a minus, but big deal. If I look at this, first term is a perfect square. Right? My last term is a perfect square. So I ask myself, I say self, is 12x the product of this, or sorry, hang on, I missed something, sorry, I hope you're writing in pencil. Is 12x double, oh come on pen, double the product, that's the word I wanted, sorry, of the square roots of the first and last terms. So let's figure that out. The square root of 4x squared is 2x. The square root of 9 is 3. If I times 2x by 3, and then I double it, I get 12x. Therefore, 4x squared plus 12x plus 9 is factors into 2x plus 3 squared. Now, again, the difference between this one and the one that I did in the previous example is, again, this difference is this minus here. Right? This guy had a minus in front of the 12 right here, and this guy has a plus in front of the 12 right here. Notice that the sign here has to agree with the sign here. That should make logical sense when you think about it. Notice the sign, let me use a different colored highlighter, green. Notice the sign of the constant, if you like the C term, has to always be plus. Could a perfect square trinomial have a minus in those spots that I just put as green? And the answer is no. How come? Because you can't times a number by itself and get a negative. Think about why that is. Positive times a positive isn't a negative. A negative times a negative isn't a negative. So a perfect square trinomial, I'm just going to keep writing notes over here because I don't need much room to actually do the question. And I'm tired of writing perfect square trinomial. Are you okay with PST? And you know we're not talking about provincial sales tax? A perfect square trinomial is always ax squared plus bx plus c, where, okay, let's turn the words that I had up here into fancy algebra. What would you say? Two times root a times root b, and by the way, if I'm going to do the square root of a times the square root of b, I can just say the square root of ab. Has to, or sorry, oh, I meant c. Square root of ac has to equal b. So let's try that for the next one. Is the next one a perfect square trinomial? And most of you are probably going, well, yeah, it is. Otherwise, why would you put it on the example page for the lesson on perfect square trinomials? Well, you never know. We might just put one on there that's wrong just to mess with you. Or maybe we made a typo. That happens. Is that a perfect square trinomial? If I took 25 and 4, first of all, are 25 and 4 perfect squares? Yes. 5 times 5, 2 times 2. If I took 5 and 2 and I doubled it, do I get 20? Yes. I guess the fact that it's negative 20 means that really I should maybe put plus or minus on here, right? It could be a plus or a minus. So this has to be, so is this a PST? So do a PST check. And I don't think I'd ever bother writing a PST check as I'm actually doing this. But let's see. Square root of 25 is 5. Square root of 4 is 2. 2 times 5 times 2 is 20. Check. Therefore, this thing has to factor into 5x minus 2 squared. Now, why is it a minus? Because that's a minus. And that's all there is to these. The goal is that you can recognize them out in the wild. It's like bird watching. You're going to sit there and go through the homework and go, aha, spotted a red-winged blackbird. Aha, I've spotted a perfect square trinomial. I don't have to think very hard on how to factor it once I notice what it is. Okay, that's it. I didn't actually put the assignment on the blog yet because I didn't have a textbook on me when I was looking at my lesson yesterday. So I have written it down now. The assignment for this is page 194. You can have some time to work on this. Numbers 4 to 8, 10, 11, 15, 20, and 21. That looks like a lot of work, but these ones aren't as long as some of the others. Like, I think some of these questions have like A, B, C, D instead of like A to H. And you have like half an hour, so you got all kinds of work time. So there we go. That's the lesson. I'll turn off the video. Oh, somebody has their hand up. I'll get to your question in a sec. Let me stop the video first.